All right. So how'd the homework go with the doubly linked lists? Not too bad. Okay, we saw that adding a tail to it actually allowed you to it would have made all the other functions a little bit easier, right? When you needed to add something to the end clearly, right? We're actually not going to go back and update our linked list to have a tail. Instead, we're going to start talking about another kind of application of linked list, and we'll implement tails into that just for time. So we'll still do it. So other applications of linked list. We have something called a stack. Okay, a stack is a last in, first out queue. As opposed to, a lot of times this is called a LIFO, last in, first out. As opposed to a queue, which is effectively a line, right? So this is a first in, first out. FIFO. All right, so these are actually implementations of linked lists, specific implementations of linked lists that are less general purpose. So if you think about the linked list we've written up to this point, we've kind of thrown everything, including the kitchen sink, into the thing. Add, remove an index, all sorts of stuff. When these guys are saying, look, we need a stack. And a stack is like a stack of magazines. When I put something onto the top, when I put something onto the stack, I put it on the top of the stack, right? When I take something off the stack, I remove it from the top of the stack. You don't pull from the middle of the stack. You don't pull from the bottom of the stack. The way stacks conveniently work is you put something on the top, you remove from the top. If you want to get the third magazine down on the top, you have to remove 2 to get to the third, right? And then you can put the other 2 back on if you want to. All right, so that's how a stack functions. So everything is add front, remove front. That make sense? All right, so with a stack, we have 3 functions. We have push, pop, peek. Okay, push. Did we do Towers of Hanoi last semester? Okay, fine. So push says add something to the top of the stack. Pop says remove and return the top of the stack. Peek says return, or we could say look at the top of the stack without removing it. Make sense? Now, the official data structures definition for stacks only require push and pop. I find peek to be pretty handy. Sometimes you want to look at what's at the top of the stack, so I include it in what I would call a required function for stacks. All right. So we're going to start building a baseline for this. I'm actually going to put it into a directory for something called Towers of Hanoi, which is going to be the first thing we're going to end up building, and I'll kind of talk about that today. It's an application of using stacks. But let's start off with simplified stacks first. All right, so let me close this. Let me actually just create a new folder here for, this is 300, right? Victor. And I'll go ahead and do actually, just so we have the pieces, I'll take you through the process of what I do to create that file for GitHub. So I'm going to go ahead and bounce over to GitHub real quick. And I'm going to create a new repository. I'm going to call this guy Towers of Hanoi. I can't make it any longer. Oh, it's just Hanoi CSC300 Spring 2020. Very verbose. Okay. And I'll make sure it's public. And I'll go ahead and I'll create this repository. And when you do this, it gives you your initial commands that you need to have in here. So I'm just going to copy, well, I don't need to copy it. So I'm going to initialize my, so I'm in a folder here. Nothing's in the folder. So ls-a shows nothing in there. I have two hidden folders. One's called dot, one's called dot dot. What does dot mean? That means this directory. Dot dot means the directory above me. So if I do cd dot dot, that takes me up one level. If I say cd dot, it keeps me right where I'm at. So you've probably seen me do things like dot slash like this and then type something. So that says look in the current directory and then do something. Because a lot of times your current directory is not inside of what's called the your path environment variable. So if I say echo path, there's this global variable called path, and these are all the places if I type in some command, like let's assume that I think there's a computer program called LOL. And I type in LOL and press enter, it's going to say command not found. What did it do? Well, it first looked in here for it, then it looked in here for it, then it looked in here, so on and so forth. All right, looked at all those places, and when it didn't find them in any of those places, it stopped looking and gave me my error message. Didn't find it. All right, even gave me a suggestion on what I might do to try to install it. But it couldn't find an LOL, but it found a GOL and an SOL and a COL, whatever. Okay, so that's why sometimes you'll see me do something like dot slash, like I did it for my push to GitHub thing, because my local directory of home / CSC300 / towers of Hanoi, that wasn't in that path variable. It wasn't in the places that it'll automatically look for. So I'm telling it, hey, I have an executable in this current directory. I want to run it dot slash is the full path to where it's at. Does that make sense? So that's, so if you do an ls-a, which shows everything, it'll show all the hidden files, including those two files that come with every directory. So we're kind of seeing the file system under the hood. And this is the same thing is true on Windows. Windows has a dot and a dot dot directory included in their file system. So when I do a git init in here, that initializes a brand new Git repository. You only do this once per repository, so you can think of a repository as a folder. So I'll do that. It says it initialized an empty Git. So if I just do an ls, I see nothing there. But now if I do an ls-a, I'll see there's a third thing in there, a .git. So any folder that has a period in front of it, by default, it's a hidden folder. So inside of that .git folder is all the GitHub repository stuff. Okay. I'm going to go back to my thing here. I'm going to take this line right here, this git remote add. This also needs to happen one time. This lets my local repository know about GitHub's link to this repository. I've created a special little container up in GitHub that knows how to hold Git repositories. All I've done here is I've created a local Git repository just on my computer. If I want this guy to know about my repository in the cloud so I can easily push to it, I'll just issue that command one time. So now this local repository knows that it has a remote repository that is at the new thing I just created. Okay? Then I can go ahead and do a git commit. This guy's. So whenever I've made changes, whatever. So usually you would do a, git add dot, but I don't have anything in this directory currently. So let's go ahead and let's create a file in my directory. Then we'll go ahead and do this. So I'm going to go ahead and we're going to open a folder. And the folder I'm going to open is Towers of Hanoi. All right, so there's this folder. There's nothing in there, but I'm going to go ahead and create a file in here. And we're going to call this guy a stack. So he's going to be stack.h. Usually your header files, these are usually lowercase. I'm kind of using uppercase because this is our precursor to classes, let's say. Actually, we are doing classes in here. So we'll call it stack.h. I'm doing C in another class. We're doing H or HPPs in here. HPPs in here, right? All right, so there's my stack HPP. And inside here, we, what have we done, like if defs? Yeah, I'll probably leave the if not defined thing out because I know that's boring. All right, we'll create our class in there. So this stuff is more of directives to the compiler that I typically wouldn't use because as the developer, I know I'm defining it. And chances are all my stuff is being contained inside of a single folder, so I know I'm not defining it a second time. But if you're working in a larger setting with a large project, you might only want this guy to get defined if it's not already defined. Okay. So we'll go ahead and I'm not going to include anything in here yet. So I'm going to say class stack. And we'll end that guy with a semicolon. And this guy's going to have a public section. Actually, I'll do the private section at the top and then a public section. Okay. Now, under the private section, if we think about what a stack is going to have, let's go back here to our design. Actually, just to finish up the Git tutorial thing here, we'll say, all right, I'm tired of coding for the day. I've done all the stuff I'm going to do. We'll come back out here and we'll go ahead and say git add dot. This adds everything that's in there. So if I do a git status, it shows me that I have a new file called stack HPP. Git status isn't part of what you'll have to do. It's just a way of showing that your Git repository, your local Git repository has updated. So then I'll do a git commit -m, call this guy initial commit. This will commit my code to the local Git repository. All right. Then this is the line that actually pushes it to my remote GitHub. Oh, I already. Yeah, that's the wrong command I copied. This is the one that actually pushes it. I already created the remote. Now I need to actually push it to the remote. So git push -u origin master. It's asking me for my GitHub username and password. All right, and if I go back to GitHub here, and I just refresh, I now have a file up here. You can do it.
GitHub might be down.
Oh, is it?
Yeah, not working for me.
Oh, yeah, there we go. Well, In any case, it's in theory it's up there, but this thing, oh, it said server error. It didn't actually go. We'll try it one more time. Yep, server error, so it looks like GitHub is down. All right, but in any case, what I'll do is I'll go ahead and I'll copy over, what was that, linked list? And I have my GitHub push file, so I'm going to copy that GitHub push file that I had from before into this local directory. And then I'll, actually I could edit it up here now. All right, so this guy, I'm removing my output file or my executable. I'm adding everything, I'm committing everything, I'm pushing everything. So all those files are still the same, right? So whenever I want to do it, I can just run that command. And that's where I would do that /GitHub push. You can find that file in the current directory. All right. So hopefully it's back up by the time we're done with class, but it's just.
The GitHub push, is that just push or is that committing and then pushing? Like how does that?
It's both. So this deletes a.out from my current directory. Then I'm adding all my files. Okay. So it'll keep track of the changed ones. Then I'm committing locally, and then I'm pushing remotely.
Okay.
Just the same 4 things I would usually
you
do.
Just do it in one command. So then to make sure that you just have to run that when you're.
Yeah. So when I'm ready to do it, I just you have to make it executable. So if you see it's currently, you see how stack is in white, GitHub push is in green on here. If I do ls-l, it shows me the permissions for these guys. So this guy is read, write, and execute. So an X means is executable. So if I wanted to change stack to be that, well, here, I'll just do it with GitHub push. So if I say GitHub push is 700, actually, let's make it 500. Now I do it ls. Actually, now it's just executable. Now it's read and executable. I took all those other permissions away from it. But usually I would have it at. So now it's just writable. That's all I can do to that file is write it. Notice it's no longer in green. I can't even read it. So, but usually the go-to move is 755. This makes it readable and executable by everybody and read, write, and executable by me. Now it's green again, so just /GitHub push will ask me that same piece of information, username, password, and do all the stuff.
I think it works now. I think GitHub.
So you think it's up?
No. Oh, no.
Yeah.
It still says it's going through.
Okay, so let's start thinking about planning what our stack looks like. So now try to, even though we're looking at a traditional data structure called a stack, try to imagine this as I'm solving some problem for work. And I need something that works this way. Something that if I add something to the top, it gets stored there, and I can keep putting stuff above that, above that, above that. Whether we're calling it a stack or we're calling it something else, maybe we're calling it a tower, hint, hint, in your towers of Hanoi. It doesn't necessarily matter. We're saying this is what I'm trying to solve. What are the pieces I'm going to need to solve it? What happened?
Nothing. He always gets like BBs in his laptop.
Yeah, I don't know why. I don't know where they come from, but he's always like pointing out that I like these like little.
Like metal things?
Like little.
Look at that, like on the side here. I don't know where it comes from.
The laptop just grows it when you order it too hard.
I don't get it. I have no idea what they are. Sorry about that.
That's fine.
It's random.
All right, so a stack, we're going to have to keep track of the top of the stack. Now, if we're kind of thinking about this in terms of our linked lists, our top, our stack is likely going to be a collection of things, right? And historically, we've called our things nodes. So I'll go ahead and give myself a node, which isn't actually going to be much different than the nodes we've had in the past, but we'll go ahead and recreate our node. So a node's going to have a payload, and we'll stick with an integer for our payload. You might find that your payload, when you start working on your towers of Hanoi, is a little bit different. And maybe instead of node, you'll call it a disk, hint, hint. You just might want to take notes on those couple of hint, hint things. It might make your homework a little easier. A tower is a stack, a disk is a node. All right, so int payload, and then we usually know about the next node, right? So we have our node pointer, next node. Now, based on the homework assignment we just did, we might say, well, maybe I want to know about the previous node as well. But we need to think about, well, how do stacks work? Well, a stack works by having to take the first thing and removing that from my stack. I'm always adding to the front and removing from my front. Do I need a previous node to do that? Do I need to keep track at the end of the list to do that? No, this is like the simplest little move for linked lists, right? So I can say, yes, I know it's possible for a node to keep track of the guy before me and the guy after me, but really, our nodes for our stacks just need to know about next node. Pretty simplified type things. All right, so we have a payload and we have a next node. So let's go ahead and build our node class. So I'll create a new file here. We'll call this node HPP. And we'll call this guy class node. And we're going to have a private section and a public section. And in the private section, we're going to have an int called payload. And then we'll also have a node pointer, maybe called next node. All right. And we'll leave the public section clear for right now. We'll add some stuff soon. Okay. Go back to our stack. A stack, we need to remember the top of the stack. What kind of animal is the top of our stack? Top is a synonym for head. So a head is to a linked list as top is to a stack. So what kind of thing is this? What kind of animal? It's a node. So this is a node pointer, right? If I'm looking at the top of my stack, I have a stack of nodes, so the top of it's going to be a node, right? That's a node pointer. So inside stack, we'll have a node pointer that I'm calling top, but understand that this guy serves the same purpose as head served. We're just using the naming conventions of the stack data structure. Okay, it's not happy with node pointing here. Why not? I have to include it. All right, so up here, I need to do pound include, and I put double quotes around it, right? And there's my node file. So now this guy's cool with it again. All right, that makes sense? So that's what a stack is right now. Okay. What else should a stack be able to do? Well, we talked about stacks right here. They have a push, a pop, and a peek, right? So I need to have those three functions at least. So I'm going to have a push, pop, peek. What is peek going to return? Okay, it'll return top. We can choose to either have it return top in its current form, which is a node pointer, or we can have it return just the payload there if we were interested. Either one is equally viable. Okay, it depends on the problem we're trying to solve. Let's go ahead and have this guy return the payload. All right, but that's not always going to be the right answer. Sometimes you might actually want the whole object because that object might hold more stuff. Make sense? So like for Towers of Hanoi, you might not just hold payload and next node. It might keep track of a couple other things that might be beneficial. All right, so we're going to say this guy's going to return the integer at the top. So peek is going to return the top of the stack without removing it. Pop is going to return an int. Same as peek, but removes it. What does push return? Void. Doesn't return anything. It does something. It puts a value onto the top of the stack. All right. So push. What does push need in order to work? Go ahead. A new node or the ingredients for a node, right? So I either need a node itself or I need the payload so I can build a node. Again, this could go either way, depending on the application you're writing. All right, so those are the three things I'm going to end up writing here at the very least. So under public, we'll go ahead and we're going to say we're going to have, let's kind of do them in the order of, actually it doesn't really matter what order we do it in. So we'll do void push, and this guy will take it an int payload. Then we'll have an int pop. He takes in no parameters. And we'll have an int peek. And he takes in no parameters. See how nice header files are since they look just like what we designed here? Nice and clean. They don't have all this other stuff in there. It's a little bit extra kind of work to manage them, but at the end of the day, it's probably worth it. All right, so I'm going to steal those three things. Go ahead.
What do you say was the second way that we can do things that's more useful for like void push? Like the second
Well,
way
instead of peek or pop, maybe these guys return the entire node.
Okay. Well, no, I was talking about the int payload. I thought you said you.
Yeah, same thing. You might have this guy, instead of taking in an int, maybe it takes in
A node.
the whole node.
Or a new, or can it be a new node, or is it just a node?
Well, he's going to take in this kind of animal.
Yeah.
Give me a node to work.
Okay.
What you pass him when you actually go to use him, you would be passing him a new node. But we'll keep it simple. We'll say you want to add something to the top of a stack. If we're creating a stack of ints, what are we probably adding to the stack? Well, we're adding an int. You wrap it however you want to wrap it. I'm adding an int to it. When I want to get it off of the stack, I want the int back. I don't care how you had it packaged, you give me my number. That's what I want. Okay? So we'll go ahead and take these three things and let's go and implement them, and then we'll start fleshing out node as we go. So we need to implement a stack.cpp. Be really nice if I can like right click on this and it says create stack CPP. First world problems. Stack CPP. We're going to include stack HPP, and then this is our stack. All right, so those are my functions I'm creating in here, and they belong to the stack class that's defined inside of stack HPP. All right, so if I'm peeking, peeking's my easy one, right? You had to make it creepy, didn't you? That one's the easy one. I'm returning the int that is the top of the stack. So in order to accomplish this, we need to add a couple of abilities to our node, because we have made these guys part of the private section, right? Just like in Java, we've said make everything as private as possible, then loosen the reins when you need to. So now we need some public accessors to these things in order to be able to do things. So one of those might be get the payload, right? So get payload is going to return an int So this guy returns the number within this node. That's what get payload will do. Because I can't access this guy directly because he is a private member of the class. So inside of my node HPP, we're going to define an int get payload like that. All right, now let's go ahead and let's start fleshing out our node CPP. So we'll say new file, node CPP, and this guy is going to include node HPP. Oh, I thought I had copied it. All right, so here's my int node get payload, and he's going to return this payload. Easy peasy. All right, so now I have the ability to get a payload. Now down here in stack, when I'm implementing peak, we can decide, are we we can decide now if we want to do any error checking. At this point, we haven't talked about managing errors. So for right now, why don't we still make, I kind of keep remembering to show you how to handle exceptions and stuff. Why don't we just assume if you're calling peak, there is a top of the stack for right now. All right, so I'm going to say, I'm going to return this top get payload. The top of the stack's payload. Assuming there is a top. Otherwise, you're going to get a segmentation error because it's going to say that this guy doesn't exist. Well, it won't even say that. It'll just say segmentation error. But it's because this guy doesn't exist, and furthermore, you can't call a function on nothingness. Only Mr. Gonzalez can do that. And I suppose Dr. Locklear would say Chuck Norris as well. All right. So that's the get payload. Notice we are returning it, but we're not disconnecting it from our list. That makes sense? All right. If I'm popping, I'm ultimately going to return this payload, but I'm not actually, but I am going to disconnect that node from the list, right? So what does that look like? Let's go back to our pictures. We'll create a new picture for our stack. We'll give ourselves, so actually let's build this guy out first. All right, so this guy is going to have a payload, so maybe this is 5. And the next node, and we'll just draw arrows for next nodes. right, something like that. So these guys attach to each other, and then we have a variable called top. And top will point to the top node in our stack. All right, so what we just did in our peek is we said follow top and get the payload from this guy. Now, for pop, we want to do the same thing, but we also want to actually disconnect this guy from the list. All right, so let's grab the payload first, the guy that we're going to ultimately return. So for pop, we're going to say int value to return is equal to this top get payload. That way we won't forget it, right? That's the value we're ultimately going to return. We can even go at the very bottom here and say value to return, and then we'll build our sandwich in between. All right, so what we need to do in the middle here is we need to actually disconnect that node. What does it mean to disconnect that node? Well, here's the guy I'm going to get rid of. So I could create maybe a variable called temp or something like that and have him point here. So now we have two things pointing to that guy, right? So once I have that, so let's go ahead and make temp point to the same thing that top points to. Node pointer temp is equal to top. Then I can say temp's next node, top is equal to temp's next node. That'll be the new top, correct? But in order to do that, a node needs to be able to set his next node. My nodes don't know how to do that yet. So I need to set my next node, so it's not going to return anything. Set next node, and this guy will take in a node pointer as a parameter. So I'll go ahead and write this into node. All right, and set next node will set this node's next node equal to whatever you passed them. Easy peasy. All right. So I'm going to ask temps, well, I'm going to say top is equal to whatever temps get next node is. Go ahead.
Why wouldn't you set it to what top's next node is?
You could. So you could say this. You could say top is equal to top. Now we need to have a get next node. Should have put that in there to begin with. So we need a node pointer get next node. So a node should be able to return his own next node. This guy will return this dot next node. So we could say top is equal to top's own get next node. That would update top. So that would make top point down to this guy.
Then we remove
Hmm.
Then we remove temp.
Well, you have a couple of options here. So I would usually set temps. I would fully disconnect this, even though it's not really needed. So I would say temp dot set next node
No.
to 0. So that will detach temp from our list, from our stack. So now temp looks like this. Now at this point in time, I could have chosen to put this line after line 13 here and use temp to get the payload. Didn't matter. We're talking about the same node in either case. This is the number I'm going to ultimately return, so it's fine where it's at. But now I want to clean up this memory. And what's our command for cleaning up memory? Delete. So I will delete temp. And that will return the memory that was used for this node to the operating system. So it can be handed out to somebody else who might need it in the future. But notice I've preserved that 5 inside of this variable called value to return before I did that. Make sense? All right, so that's pop. Push says we're going to add something onto our stack. So we're going to go ahead and we're going to create a node. Now we're at the point where I need to create nodes. I haven't written a constructor yet, have I? So what's my constructor look like for a node? Oh, I don't need a return type for it. So there's my constructor for my node. So to create my node, we'll just put this at the top for node. We're going to have our node. And this guy will set this payload equal to the payload that was passed in. And then we can go ahead and say this next node is equal to null. Should be that anyways, but that just emphasizes the nullness. All right, so that allows us to create a node. So now I can say node pointer n is equal to new node passing it payload. And when I push something onto my stack, where does it go? Go ahead. The top. Goes at the top of the stack. All right, so let's just assume here, I'll reuse this guy. Oh man, did you see that ninja move? Man, that was total savant mode with Keynote. You don't seem impressed, Clancy.
I just love Noah's face. He just goes. I think that was the savant mode that made us laugh. He kept saying that on Saturday. He's like, I'm about to go savant mode.
What does savant mode look like for you, Noah? Well, I usually I fart a little bit.
Starts programming with his mind, levitating.
Mr. Gonzalez does it with the laptop closed.
You open it up, the program's already written.
Yeah.
There was a game for Nintendo, Mike Tyson's Punch-Out,
Yep.
that they later, after his whole prison thing, they re-released it as Punch-Out, where the end guy was a white guy. Same moves and everything.
It's your dream.
Yeah. But the original Mike Tyson's Punch-Out, there was one of the fights was, I think his name was King Hippo.
Yep.
My brother and I couldn't figure it out. I mean, we were little kids. My dad told us that he could beat him with the TV off. We were trying to beg him to tell us how to do it. We believed him. 100%. Dad can beat it with the TV off. It's amazing. Savant mode. That's when it was born.
Yeah. That's all
This was like the old tube TV that was made of wood.
Yeah.
You have to hit him
I
with
can
an
get
off
I can get to like the last few stages of that game, and then I'm like, I can't do it. Yeah.
You just need, yeah.
I might even remember the Mike Tyson code. I've beaten it a bunch of times, like 007 737 5468,
Yeah.
something like that.
I think it's funny because halfway, like whenever you're like trying
What's
to,
up?
That's the map mode right there.
I think it's funny, like half the game for Punch Out is just like a McDonald's ad. It's like, make sure to join the McDonald's Fun Club. It's like, okay.
Well, it happens sometimes.
All right, so we want to add this guy to the top of our list, right?
What'd you say was the Mike?
007 547.
Close.
You said 007.
And this is for Mike Tyson, or is this for the
Mike Tyson's Punch Out.
007 373
5468
5963.
5963. Yeah.
I'm so
Pretty
impressed you
close.
got that.
That was
that
pretty
bit of
close.
it.
What year did that game come out in?
19, I think.
87.
Oh, geez, that's
87. So that's knowledge. I would have beaten it the first year it came out.
Yeah.
Whatever.
So that's 33-year-old. That's a 33-year-old memory.
Well, how many times did you go back to the Mike Tyson fight? Is the question.
A couple times.
Couple times.
Yeah.
He one-shot you.
Yeah, his first, in the first, I think, 250 minutes of that fight, he won in round one, he can one-shot you, basically. Every punch, one shot. If you can survive that, he's a bit better. No, seriously.
All right, shut up. All right, let's add this guy to the top of our stack. All right, so we have a new guy here. We just created him, node n. So here he is right here. There's our node n, and we want him to become the new top of our stack. So how do we make that happen? Well, we can't just do this. If I do that, what happens? I lost the top of my stack, right? So I need to set n's next node equal to tops next node. All right, but we only want to do this if top points to something, right? Because if top was nothing, if my stack was currently empty, then I just make top point to this guy and I'm done, right? So if top, so we can either say if top is something added, or I can say if not top, set top equal to this guy. So I could say if top, this means we have at least one element on our stack. Then what we'll do is we'll set n, set next node to top. And then we'll set top equal to n. So that's this move right here. Set n's next node equal to the same thing top points to, then set top to point to n. And that will add him to the top of our stack. Else, that means we have the empty stack where we just where we say this top is equal to n. Make sense? All right, but anyway you cut it, when we're done with that, top always points at the top. Now we probably want to have a way of displaying our stack just so we can see how it is outputting, how it's functioning. So we'll go ahead and in our stack, we'll go ahead and give this guy a void display function. And while we're at it, why don't we go ahead and give him a constructor. And stacks don't need any parameters in order to be built. They start off as an empty stack with nothing in it. All right, so I'll copy this guy. So there's our constructor for stack, and our constructor for stack is just going to set this top equal to nothing. That's the empty stack. Go ahead.
So are stacks to nodes like array lists are to arrays?
You mean our stacks to linked lists?
Yeah, yeah.
No, because stacks still follow the exact same internal mechanism of linked lists, although I think we saw array lists do as well. But they are, the difference between an array and an array list was that array list can dynamically grow and shrink. Stacks and linked lists both grow and shrink. The difference is a linked list is very general purpose. We could add stuff to the front, we could add stuff to the end, we could add stuff to the middle. Where a stack, we're always adding it to the front, we're always removing it from the front. It's just a simplified version of a linked list. All right, so if I'm creating a new stack, we just set top to nothing. For display, what do we need to do? Again, we can assume, well, I mean, if we want, we can say if this top, display it, else. We can do something like standard cout empty stack. And I think in order to do this, we need to include IO stream. So that standard cout is inside the IO stream. Notice we have the angle brackets here, so that's part of the C library, C++ library. Well, there's no reason why I can't just put the backslash in there. It's fine. All right, so if I'm inside this if right here, that means I actually have a list I need to go through. So I want to have a stack I want to go through. So I want to start at the first thing and keep walking down, displaying each one. And I'll display them one per line maybe just to kind of show the stack as a stack. All right, rather than all of them right next to each other like we did with the linked list with the little arrow. I think we did that with the arrow. I didn't do that? No, whatever. Oh, you want to see the arrow one this time? I want it to look like a stack. Make it look like a stack. All right, so we'll have a node pointer, cur node. We'll start this guy off at the top because we don't want to change top, right? We want something that's going to walk our list until we're done. So we'll say while cur node. Oh well, we'll just say while core node. So while cur node, while it's a thing, we want to go ahead and print it out. And what are we printing out? We're going to print out its payload. So cur node get payload. And then we'll set cur node equal to cur node's own next node. So we'll start at the top. As long as there's something in there, we'll go ahead and we'd only be in here if there was at least something in there the first time. we could say, well, then we didn't need the if else structure, but then we'd lose our opportunity to say empty stack. Whatever. All right. So as long as there's something in there, we'll go ahead and print out the payload of it and kick it down the line. Then we'll update cur node to point to his own next node. Zip him down the stack.
If cur node is the last node, what is it getting sent to?
You mean right here?
Yeah, if it's the last one.
Well, if it's the last one, cur node's next node will be null. Because that's the default value for a node's next node.
So, and then next time through that loop, it'll see cur node as null, so it will stop.
Correct. Yep, because the next time through, what he's saying is the next time through this while loop, is cur node a thing? No, it's not a thing, so we'll fall out of the while loop. All right, so that should display it. All right, we'll go ahead and create our driver CPP. All right, we're gonna go ahead and include stack HPP. We'll also, actually we won't need IOStream here yet. And we'll go ahead and just say int main. And at the end, I'll return a 1, everything went fine. So that might be your like stock main method for your C++ program. Optionally, you could have it take in the command line arguments, but we're not using command line arguments right now, so we can just choose not to. All right, and what are we going to do in here? We're going to go ahead and we're going to create a stack pointer called the stack. This guy's going to be a new stack. And then if we go ahead and say the stack, display, we should get empty stack. All right, so we'll go ahead and test this. So there's my code here. I will do a G++ star dot CPP dot slash a dot out. There's my empty stack.
Is it working?
I don't know. GitHub's working? All right, well, yeah, well, we'll push it here in a few minutes. All right, so that's my empty stack. Now, if I want to go ahead and start adding some stuff to it, I'll say the stack push, and let's push it to because main returns an int in on Unix systems. So 1 means everything's fine. Or you can actually, 1 can mean anything you want. Just return an int. We're not using it. So actually, a lot of times 0 means everything's fine, even though we usually think of 0 as being false to 1 being true. So pick your poison. This is kind of like a return code, where 0 might mean everything's fine, a 1 means this went wrong, a 2 means this other thing went wrong, and 19 means something else went wrong. You know, something like that. So we'll push 2, 3, 4, 5, and then display. Remember, this is always adding to the front, so my stack should be 5, 4, 3, 2. There's my 5, 4, 3, 2. Now let's test our peak. Now in order, peak's going to give me back an int. I want to be able to display it, so I'm going to have to give myself IOStream.
You need to give yourself IOStream if stack has IOStream.
Does stack have IOStream? That's a good question. I don't know if I need to or not. I think I do. I think it's a namespace thing.
Okay.
But it's a good question, and I can't necessarily give you a great... Yeah, I need it. So I'll go ahead and display the stack peak. I'm just going to move the display after this. No, it's from. It actually is from Final Fantasy, but it's also it's also in Mike Tyson's Punch Out
Really like the original Final Fantasy.
when he's doing the jogging.
Oh.
Dun, 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 dun. Oh yeah, it's so good. You have a playlist. All right, so I'll just kick it down. I'll kick it down a line here just so we can see. So I'm going to go ahead and peek the top of the stack and print it out. Remember, peek does not modify the stack. So I should have my original 5432, where 5 is the top. So the output of this should be 5432. So there's my 5432. As opposed to if I pop now the 5 should be gone. So it'll just be 432. So it'll be 5432. Here's my 5432. Okay. Last thing. This is underwater hockey, by the way. It's a real thing. Let's see. Towers of Hanoi. So, for Thursday, you're going to make a text-based version of this. Create a version of Towers of Hanoi. You don't have to follow all the rules yet. All right? You're going to see what I mean by this. So, for Thursday, you're going to have 3 separate stacks. These are our towers. All right? Actually, following the rules will actually make it easier to begin with. So you do have to follow the rules. So we have 3 towers. Each tower has 3 disks on them. The goal here is to get, well, the starting tower has 3 disks on it. The goal is to get these 3 disks over to this far right tower. But the rule is you cannot put a larger disk on top of a smaller disk. That's an illegal move.
You can only take one at a time.
Yep, you can only take one at a time. So on and so forth. And I'm not doing this in the most efficient way, but it'll get there. So there's my win. All right. Yeah, I know you can. All right. So let me actually think about this. For Thursday, make it so that you've represented your towers, you've represented your disks, and you can, because I want to teach you how to do I/O first, and then we can do the other complex things. So make it so that you can issue commands. You can show the board for Towers of Hanoi, and you can say, I want to move from Tower 1 to Tower 2, and that'll pop from Tower 1, push to Tower 2. I want to move from Tower 3 to Tower 1. That'll pop from Tower 3, push to Tower 1, and be able to display the current state of the board. All right? You do not have to apply the rules, so like in your version, you can put the disk that's larger on top of the disk that's smaller. All right? And you are manually issuing those commands to pop from Tower 0, Tower 1, Tower 2, as opposed to reading in from the user. We'll learn the additional skills we'll need, so over the weekend we'll finish off Towers of Hanoi. Make sense? So give yourself a working text-based board for Towers of Hanoi that allows you to manually move things from one tower to another, displaying some sort of version of your towers. I wouldn't spend too much time making your board look super pretty. You can just have everything left justified. Otherwise, you can play with spacing and stuff to make it look like a tower, because, you know, you're probably going to have, you know, these things. You're not doing graphics here. So you're probably going to have your towers displayed as a bunch of underscores, a bunch of underscores, a bunch of underscores. And then when there's discs on top of it, maybe you have 3 equal signs, or maybe this is 1 equal sign, and this is 5 equal signs, something like that. So you're representing your discs with just text-based equal signs, because you don't have graphics at this point. So you don't necessarily need to center this smaller 2 equal signs or 1 equal sign on top of the 3 equal signs, for example. If you just left justify them, life will go on. All right, so don't spend time making your game look too pretty, or you don't have to. All right, questions, comments, concerns, bribes. I'll go ahead and push this up to GitHub. You said it's working now. All right, so now it's up on GitHub. So I should be able to refresh this and see it. And there it is. Okay, remember, today, student, faculty, staff, Bible study, God and Grub. Go to the cafeteria, sign in, get your free lunch, take it down to the terrace room from noon to 1. I will see everybody on Thursday.